Okay, so let's go ahead and continue on acids and bases. Um, so what we're going to talk about now is the autoionization of water. And basically what that means is water will undergo its own dissociation. So what we have is that one of my water molecules will act like like an acid right here, and the other will act like a base. So this will donate the hydrogen, become hydroxide, and the other one accepts that hydrogen and becomes the hydronium ion. And typically what I've drawn down here below is that you'll see us basically talk about the autoionization of water, where we just dissociated here. And typically for that, we find that we can use interchangeably the H plus with a hydronium ion. When my water dissociates, then the K value, my equilibrium value for the dissociation of water, is going to be equal to the concentration of my hydronium ion times the concentration of my hydroxide ion. And at 25 degrees Celsius, we know that the value of K is equal to 1 times 10 to the minus 14, which means that the concentration of my hydronium ion is equal to the concentration of my hydroxide ion, and that's going to be equal to 1 times 10 to the minus 7. So now that we know that, just so you know, I've written down below the dissociation where we didn't have it react with two water molecules itself, but it just comes apart. Now, when we do this, what we see is that a little p means negative log. So pH is the negative log of my H plus concentration, or my hydronium ion concentration. pOH is equal to the negative log of hydroxide concentration. pKa is equal to the negative log of Ka. If we talk about pKb, then it's going to be the negative log of Kb, etc. Now at 25 degrees Celsius for water, the pKa is going to be equal to 14. That's also equal to, when you see the W here, it's specifically for water, we can also write pKw. And what we find is that pH plus pOH is going to be equal to 14. This allows us, if I have a certain pH, allows us to determine the pOH of that solution, or vice versa. So let's go to strong acids and strong bases. So remember, when we talk about a strong acid or a strong base, these are strong electrolytes, and a strong electrolyte essentially dissociates completely when dissolved in solution and when dissolved in water. When dissolved in water. So that means if I give you a 0.1 molar HCl solution, that means I have a 0.1 molar hydronium ion concentration and 0.1 molar chloride ion concentration. So we have 7 strong acids. Typically, we have a high value for Ka for chloric acid. So you'll see some variability on what we call, it's either 6 or 7, but I typically include this. So we have hydrochloric acid, hydrobromic acid, hydroiodic acid, sulfuric acid, nitric acid, perchloric acid, and then chloric acid. When we talk about the strong bases, again, they dissociate completely. Typically, it's going to be your group 1A metal cations along with hydroxide, so lithium hydroxide, sodium hydroxide, potassium hydroxide. You have your rubidium hydroxide and cesium hydroxide with limited solubility. So it doesn't take much before these begin to precipitate out. But the solubility runs to about 0.2 molar, could be a little less. So we have calcium hydroxide, barium hydroxide, and strontium hydroxide. So what about other acids and bases? So other acids and bases that we need to keep into mind are the weak acids, and then we'll go into weak bases. So the weak acids, if you see an acid, it's not one of the 7 strong acids that we had previously listed. Those are typically going to be weak acids. Also, they could be the conjugate acids to a weak base. So remember, weak base gives you a conjugate weak acid. Weak acid gives you a conjugate weak base. If you have a strong acid, then you have a negligible weak base. If you have a negligible acid, then the conjugate base will be a strong base. Okay, and this is our typical equilibrium reaction that we write. We have a weak acid, and here's my Ka for the acid dissociation constant, my equilibrium constant. Let's go ahead and take a quick peek at weak bases. Our classes of weak bases will include amines. These are nitrogen-containing compounds. So ammonia is related to the amine. So this is a typical amine that's called methylamine. And when it's in water, it will basically react with water, do a hydrolysis. I'm lysing the water. I form hydroxide, and I form my methyl ammonium ion. And so this is my Kb products over reactants for this particular base. We can also take a look at the conjugate base of a weak acid. So there are quite a few, and what you have to do is take a look at the acid. If you don't know the base, look at the acid and determine if it's a weak acid, so then you can determine if you have a weak base or not. So in this case, hydrofluoric acid is a weak acid, so fluoride ion will be a weak base. So it will react with water to form HF and the hydroxide. And this is my Kb equation for it. The general format for base hydrolysis is your base plus water will give you Hb plus and hydroxide. And this is your general format for your Kb equilibrium equation. So let's take a look at the relationship between Ka and Kb. So for a conjugate acid-base pair, if I write these two equations down for my conjugate acid-base pair, what would happen if I multiply the two together? And when you multiply the two together, you end up with the following. Ka times Kb is going to be equal to 1 times 10 to the minus 14. So we can, from this first equation, determine Ka if I know the Kb for the conjugate weak base, or if I'm giving Ka, I can determine for the conjugate weak base what the value for Kb is using this first equation. It also then is true that pKa plus pKb is equal to 14. So what we'll do is we'll stop here, and in the next session, talk a little bit about the effects of structure on solubility.